Hello everybody and welcome back to the first video of Biostats. This should cover all the content for quiz 1 and for exam 1. It's only about the first 2 weeks of content, so this might be a little on the shorter side, but you never know when it comes to these math videos. But the things I want to talk about are data types, error, p-values, standard deviation, z-test, um, and then t-test as well. The different types of t-test, because there were a few. Let's just start off with some definitions. This is a pretty basic slide. Descriptive statistics are kind of models that describe data. Pie charts, bar charts, anything that's really a picture is descriptive. Inferential are models that predict uh, like a like an outcome based on a sample of data. Um, so a good example of this are population parameters are things that are known, like they've been established to be true across an entire population. In people, this is generally impossible to do because getting every person as a data point would be nearly impossible going to every corner of the world. But let's say there's like an endangered species that has like 30 turtles and we know where all these turtles are and we're like measuring shell size. That could be a population parameter because we know every single turtle in existence. What we usually do for um, things like people, though, are we use sample parameters, which are called statistics, just because there is no physical way we can get every human in a study. It's just impossible. Alternatively, we could do like every human that's age 120. That could actually be a population parameter because we can probably find, I don't know how many people are 120 right now, if there even are people that are 120 right now, but that's such a low number that we could reasonably round all of those people up if we wanted to. So I hope that helps with those two kind of concepts. Discrete variables are basically qualified or qualitative data characterized into sets. So like whether or not you have a college degree. That's a very arbitrary like yes or no thing. So that's like discrete. Same with marital status. Like you're not really ever half married. I guess you could have like a very rocky marriage, but that's still either married or divorced. Uh, and continuous variables are quantitative data. So think of something like height, weight, or even like a percent score in an exam. These are all numbers. They aren't really categories, and they all kind of like can compare to each other based on these numbers. Um, an interesting example Dr. Go pointed out in class was you can kind of like there's some variability between discrete and continuous variables because if you use a scale of like 1 to 5, um, that's more categorical, right? Because one is like if you're rating an experience 1 to 5, one's like you've had a terrible experience, five is like you've had an excellent experience. But like a 0 to 100, in your mind, there's probably not a huge difference in those categories. Like if you give it like a 37 out of 100 or a 38 out of 100, like obviously a slight difference. So generally, just with what our minds can process, I would say that if it's five or less, it's probably discrete, and if it's more than five, it's probably continuous. It's not a perfect analogy, but just something to remember. Next up, independent variables. This is the variable in an experiment which is kind of changed to test a condition. You could think of like, let's say you were testing the dosage of a medication and then its effect on blood pressure. So you could change that dose, let's say 10 milligrams, 20 milligrams, 30 milligrams, and then that would be your dependent or your independent because you or yourself are changing it. Your independent would then, or no, I'm sorry, your dependent would then be your blood pressure. Dependent would be blood pressure. Independent would be dose because I know I've already tripped over my words like twice. Uh, Dependent would be blood pressure as it changes with the independent variable. The blood pressure might change based on the dose, or it might not. It depends on if the drug works or not. But yeah. Next up, types of data. Nominal data is categorical data. I think this is one of the big keys for this is and the fact that it has no implied order. So again, going back to our example of college degree and marital status, there's not per se an order to this. I guess you could make the argument like a bachelor's degree versus a PhD degree, but I more meant in the sense just like a biology degree versus a chemistry degree. Like there's no real order of those, and they're broken into categories. Ordinal has an implied order. I think the best example of this are letter grades. Obviously, like A, B, C, D, and F are kind of arbitrary, but there is an order to them, like A being at the top and F being at the bottom. Interval data is a little tricky to compare to ratio data But there is one key difference, and that's that ratio will have a zero. Interval has implied order as well as a range. I think a really good example of this are just like a PCAT or an MCAT score, or even like an ACT score. There is no zero in these. Like I think the minimum ACT score you can get is like a 12 technically. It's not zero because they're always gonna like base it off not zero. And I don't know why they do that. They just kind of do. I think it's to curve upwards to like support the people at the top, but you don't ask me. And PCATs are the same way. I forget what our PCAT's out of, but there's like another score that's not zero, that's the baseline. Like you can never get a zero on the PCAT. You could get a 0%, but that wouldn't be a zero. Um, Ratio, on the other hand, does have a zero. So this could just be like a normal test score. You could get a 0% on a test. I think a really good example of this, or at least to differentiate these two, another one at least, is like Fahrenheit versus Kelvin. Kelvin obviously measures off like an absolute zero scale, but Fahrenheit we have, it starts at like an arbitrary value, and we have values for like freezing water, boiling water. But our 0 degrees Fahrenheit obviously is not like as cold as it can get, whereas 0 degrees Kelvin is as cold as it can get. So that's kind of one I like to remember. So yeah. So next up, let's talk about types of sampling. Uh, there will probably be a question on the exam about this, so I would kind of try and keep these straight. Random sampling is just what it sounds like. There's not really a selected order. So like every condition you're testing for, every participant has equal chance of being selected. So this could be like going back to our example of testing people. Let's say you want 100 participants from around the world, and you somehow have a way of contacting and testing like all 7 billion, 8 billion people that are in the world right now. They have an equal chance. That'd be completely random sampling. Um, Selective sampling, on the other hand, is similar to random sampling. Uh, it's more along the lines of like a pre-met condition. So the one Dr. Go gives in class are like, you only test patients that visited the hospital on this day. These people are random in the sense that you made no effort to group them yourself, but based on the conditions of the world, they just happen to be in this place at this time. That is how you chose your sample. So they do have like a condition they are grouped by, but it's not exactly like a condition that they each possess. Being at the hospital isn't like a trait unique to them or like unique of their individual person. It's just happened to fall that way on that day. Um, Systematic is pretty similar to selective. It's more like think of this now as like you randomly select every fifth person that enters the hospital that day. Again, a pre-met condition that they can't control. However, now you have a system for specific people in the hospital. This isn't too much different than selective sampling because you could make the argument that this even is selective sampling to an extent. Kind of like a square rectangle argument. The systematic sampling can be selective and but not the other way around. Um, but basically, you're just selecting based on a system, but it's still random selection. Um, the next two are a little bit different. Stratified sampling it is random selection, but you have a pre-met parameter. So I think a really good way to describe this is like age groups. So let's say we have patients ages 0 to 20, 20 to 40, or 21 to 40, 41 to 60, etc. You group everybody in the world like that. Then you randomly select from those groups. So let's say you take 5 people from each one of those groups. These people are based on a condition that they share. It's not like going to the hospital that day. These people all have like an inherent trait about them, and the fact that they are ages like 0 to 20 or like 21 to 40. And then you pull random from that, but like you're going to get an equal amount of people in the 0 to 20 age group, an equal amount of people in the 21 to 40 age group, etc. Whereas before, like if we randomly selected 100 people, there is a chance that like we just get all 60-year-olds. It's not a very high chance, but there's a chance. Cluster sampling is like stratified sampling, but a little more extended. You start off with a condition. You could do the age groups again we just talked about, but then you have another condition. So in this case, you could do like hypertensive status. So you initially divide everybody into these groups, but then from each group you want 5 people that have hypertension. So then you break it down even further into like, let's say out of 0 to 20-year-olds, let's say there's like, I don't know, 1.5 billion of them in the world. Probably not a lot of them are going to have hypertension, probably a lot less. So we'll say like, I don't know, 100 million. have hypertension, versus like the 41 to 60 year age group. Let's say 1.5 billion again, just for their total population. If we break them down, probably a lot more have hypertension. So we'll say like 1 billion of those adults have hypertension. So you can see that like the subgroups inside the groups might have different relative sizes, but at the end of the day, it's still kind of random sampling once we're through all the group. So that's how sampling works. Next up, I'm going to go over some descriptive statistic, like just charts, just in case we get like a multiple choice question on this. Um, this is called the data matrix. It basically just shows the frequency of an outcome versus I guess weight of the outcome would be an okay term here, in the sense that like based on these numbers, weight 14 showed up 2 times versus weight 17 showed up 6 times. And these are all the same data points. This next one is called a histogram. It's kind of just like a bar chart, but it goes up. There's a bar for each condition, and there aren't bars between conditions. Next up is a frequency polygon. It's basically a line graph, but since like we're not per se graphing an equation, we're not really looking at like a zero value, or I guess this 0 would be 13 if they're spaced 1 apart, but it's essentially just for the x-axis that we have data for, in this case, which is 20 through 14, or 14 through 20. This next one is called a frequency distribution, a cumulative frequency distribution. So a little harder to understand, but I'll try to explain it to the best of my ability. For let me erase the data matrix because this actually makes it a little easier to see. For people that are, we'll just say that X is ages. For people that are aged 14, there's 2 of them. Now, for people that are aged 15, there's 3 of them. But people under 15, there are 2. So for 15, we put 5. And it's basically climbing like this. So for our next, we now have 5 total people aged 15 or younger. For age 16, we have 5 people. So you can see this jumps up to 10 because we have 5 new people and then 5 old people. And essentially, this will go up to the total number of participants, which in this case is 25. You could also do this with percentages, percent of the population. I feel like that's a little more common, but for an example like this, that's like a really small sample size with really distinct categories, I feel like this works a little bit better. Next up, just some definitions kind of on what you need to know when we're solving equations with statistics. Some terminology. So a data fact about a population is called a parameter. This is something we know. It's standard. Whereas a fact about data we know about a sample is a statistic. So most things that are generally calculated in like studies are statistics because almost all of them are samples. Again, if it's like, it goes back to our turtle example where we know about all 30 turtles, then it could be a parameter. Because of this, some of the math symbols we use are different. So the mean of a population is marked as mu, and then a sample is x bar. Standard deviation is sigma, variance is sigma squared, whereas a sample standard deviation and variance is s and s squared. And then this one is looked at a little bit less, but n in a population's capital, in a sample it's lowercase. I would say definitely remember like sigma and mu and x bar. I don't think he's going to be as hard when it comes to number of samples, and you're almost always safer just writing lowercase n because you're usually talking about a statistic in a class like this, or a sample in a class like this. So yeah, that's how I would do it. But I mean, just, it's one extra thing to remember also, so it doesn't really matter. Next thing is data can be skewed one way or another. A negative skew looks like this, or actually, let's talk about normal distribution first before we talk about skew. The middle is normal distribution. This is how most data will fall in most populations. There's a few things to note about it that are really important. It is unimodal, meaning it only has like one kind of hump or one kind of like centralized area. It is perfectly symmetrical, meaning its mean equals its median equals its mode, in this case. And then when you add up all the probabilities, let's say this is a probability of like 1, this is a probability of 0. Actually, no. I'm not going to do it that way because that makes a little less sense. Let's say this measures IQ. Let's say it's like 200 over here and like an IQ of like 0 over here. population is going to fall around 100. And let's say this line is like, I don't know, 50% of people have IQ 100 down this middle line right here. This assumes that these areas right here have an equal amount of people in them. So this will be 50% less. This will be 50% more of the remaining samples. And what this will kind of allow you to do is ignore this 50% actually. I think I'm explaining this very poorly. But just in the sense that the area under this curve will equal 100% of the population. That's really the big takeaway. The most people will be at a IQ of 100. And then far fewer at an IQ of 200 and far fewer at an IQ of 0. I think that's just the best way to explain that. So now that we know about normal distribution, this is kind of what we want to see in most data. It can have skews. So a negative skew would mean that not much of the population's in the lower end, statistically. So this could be something like age of people living in a retirement home. There probably aren't many 0-year-olds living in a retirement home versus 100-year-olds. Because, yeah. So this is why this data could be skewed. Versus the other way, this could be ages of people in a daycare. So probably a lot more infants than elderly. Certainly more so. This would be a positive skew. And obviously that data would not be as clean as this. But for the sake of the example, just kind of think like, why is this data moved this way? And that can kind of help you like logic it out. Something else just while I'm on the slide is talking about standard deviation. When it comes to things like this, standard deviation is kind of like the area under a certain curve from the mean. The mean in a normal distribution will always be the center. And then the area from 100 standard deviation above the mean to the mean is 34% of the population. Same with 1 standard deviation under the mean. So this is like 68% of the population will always fall within plus or minus 1 standard deviation of the mean. 2 standard deviations away from the mean, you have this 13.6%. Now this is additive to this 34%. So if we're like counting distance away from the mean, this then becomes even greater. So it's like 34 plus 13.6. It's like what, 48? So if you're over here, you're 48% away from the mean. And you can kind of use these like categorically, essentially, because standard deviations, they're arbitrary, right? They're the average distance away from the mean on a normal distribution, but they will generally still follow this population model. I believe it's called the it's 68, and then let me just plug this to my calculator really quick. There's like a rule for it in statistics, and we don't really talk about it in this class, but you certainly could. Yeah, it's the 68, 95, 98 rule. And it essentially shows this is how many people fall within, what percent of people fall within 1 standard deviation of the mean. 2 standard deviations is 95%, 3 is 98%. And you're never going to quite get to like 100%, but you'll get like close enough. How you calculate a standard deviation is, this is how you do it in a sample. This is sample standard deviation, if you remember that S from above. And you have this term right here, this n minus 1. This will actually be different in a population versus a sample. In a population, this is just n. And what this n minus 1 is this is something called a degree of freedom. N minus 1 equals degree of freedom. And there are different degrees of freedoms for different statistical tests, but just if it's a sample, you always assume it's a little bit more skewed. It's a little bit more off because it's not fully representing that population. And obviously, if your sample size is bigger, that minus 1 matters a lot less. But let's say your sample size is 3, all of a sudden, like, that's going to make a huge difference to your data. Which this n minus 1 kind of tries to account for that that variability and that inaccuracy. This is called the variance. Remember the sigma symbol is your population standard deviation, and this is squared. Or I'm sorry, this is your standard error of the mean, not your standard deviation. It's kind of like your standard deviation, but the standard error of the mean, this is variance, which is s squared. And it'd be sigma squared in population. Same thing with this n minus 1. Standard error of the mean takes your standard deviation, this is a population standard deviation, and divides it by the square root of your number of samples. And you can see this isn't an n minus 1 because it is a population due to the sigma. But let's say we were writing for a sample. It'd be Sx equals S divided by n. Or it's actually just n. And the reason for that is you don't technically need to do like the error is accounted for in different ways when you're using the standard error of the mean in a problem like this. So that's actually something very important to point out, is this will never be n minus 1. This will always just be n if it's standard error of the mean. But if it's standard deviation, then it can be n or n minus 1 based on if it's a population or if it's a sample. Okay, so now let's just work through some of these kind of concepts. I know on the previous slide I kind of started explaining what they were. I think it's easier if I just show it off, honestly. So I've got a list of numbers here. Let's talk about mean, median, mode first. So median, I line these up really easily. The median's 5. It's an odd number of numbers, so we don't need to really worry about taking the average. And the mode is also 5. It's the number that occurs most often. There are 5 5s here. There's 4 or less of everything else. And then the mean, believe it or not, is also 5. I believe these numbers add up to like 95, and then there's 19 of them. So yeah, 5. Cool. Now we can move on to the cooler stuff. Let's start with standard deviation. So standard deviation, if you remember from the previous slide, and this is a population. I'm going to do this for both populations and statistics, or and samples, but I'll go a little faster on samples because they're very similar. Standard deviation equals the sum of your sample. And when I say your sample, I don't mean like this kind of sample. I mean more like your, I think subject would be a better word. Let's just say we pick this random 4 minus the mean, which is mu, over n. So if we do all that, we get, and I'm not going to sum all this. That seems like a lot of work because basically you need to do this. Oh, and this is squared, by the way. Sorry about that. It's the sum of the differences squared. So we like have 3 minus 5 squared plus 3 minus 5 squared, and then eventually it gets to plus 4 minus 5 squared. And that's just a lot of work. So I'm not going to do all that, but essentially what it comes out to in the end is we get our n in our denominator is 19, and I believe I wrote this down correctly. Actually, let me run the math really quick because I'm curious. So these would all be minus 1, so this is 4, 4, and then these would each be 4, so it's like 12, 12. I guess I am really writing this out. That's crazy. So yeah, that's like 32. Okay. So we have 32 is the sum over 19. This comes out to be a not very nice number, but 32 divided by 19, square root of that, 1.68. Okay, so this is 1.29 is the standard deviation, equals this. So not a very nice number. The variance is nice. The variance, as you can see, is just the standard deviation squared. So this squared, we actually never need to take the square root of this. It's not a much nicer number because it's still 32 over 19, but 32 divided by 19 is that 1.68. So now let's talk about the standard error of the mean, which, if you remember from the previous slide, is sigma over the square root of number of samples. So in this case, we have our standard deviation of 1.29 over the square root of 19. So 1.29 divided by squared 19. We get 0.3. Okay, so now let's move on to samples. So I'm going to move a little quicker this time. So S equals similar thing, different symbols. In this case, it's not mu. We have x bar, so the sum of xi minus x bar. In this case, we have that degree of freedom I was talking about. It's over n minus 1. So this is going to be divided by 18. So in this case, we have the square root of 32 over 18 for our sample standard deviation. And this equals so a much nicer number, actually. This just comes out to 4/3, or 1.33 infinite. For this sample standard deviation, or this sample variation, it's also nice. It's just 32 over 18, because remember, we can just square that and get rid of it. In this case, we get 1.777 infinitely. I believe that's 1 7/9. Somebody can tell me that down in the comments if they want to take the time to do that. Now here's where the last step gets weird, and I sort of started explaining this on the previous slide, but I think I can do it better on this slide. For your standard error of the mean, or your standard error, sorry. I keep saying standard error of the mean. This is standard error right here. And then this will also be standard error. Not standard error of the mean. I don't know why I keep saying that. So basically, standard error, standard error. This will be your sample standard deviation over just the square root of n. So even though we have the degrees of freedom over here, n minus 1, why don't we do it here? The reason we don't do it here is because we already have. To get this in the first place, we already did that n minus 1. It's already been accounted for. So this will always just be the square root of n. So we have our 1.33 over our square root of 19, not 18. And this will get us 1.33 divided by 6 squared 19. A very similar standard error of the mean, 0.31, which kind of makes sense because the only real difference between these two problems is just that degree of freedom. This simple change, and it would also make sense that this one standard error is a little bit higher than this one, and that's for the fact that if something's in the denominator and it's lower, so like for example, we turned our 19 in the denominator on this side, which would make a lower number, into an 18 with that n minus 1. 19 minus 1 equals 18. This is slightly higher because of it. So that's standard error, variance, standard deviation, and then like mean median mode. Okay, so now let's talk a little bit about hypothesis testing. In science, there's two main types of hypothesis, or rather categories they fall into. There is the null hypothesis. This is usually represented with H subscript 0. What this means is there is no statistical difference between your starting condition and your tested condition. So let's say we're starting a new blood pressure med, right? Let's say all the patients we start with have a blood pressure of like 140, I don't know. Then we have our test condition. So the null hypothesis states that our new drug, the new thing we're testing, it's not going to change that, or it's not going to change it statistically significantly at least. So let's say we go from our 140, and this drug actually makes their blood pressure pretty consistently 139.99. It's like, yeah, that's a difference, but not really enough of one to be statistically significant. So in this case, we'd accept our null hypothesis and basically say nothing happened. Not that nothing happened, or just nothing statistically significant happened. The alternative hypothesis, this H subscript 1, means the opposite. Let's say this blood pressure med, we do it, they start at 140. Now let's say we're consistently getting 120. That's a pretty significant increase, or at least it can be based on the sample. But in most cases, like that would be a significant increase because that's something that's difficult to do in people. Um, this would be statistically significant. It'd be an H1. Alternatively, let's say we give our new medicine and their blood pressure rises to 160. This is also statistically significant. So we could accept an H1. It's just unfortunately not the direction we wanted to. And that'll go into one-tail and two-tail test, which I'll talk about in a little bit. How we can kind of design studies to avoid a conclusion like that. But yeah, that is a possible thing that can happen. And then this chart right here sums it up pretty well. Um, this H0 will usually fall in this range. And anything outside of that range, so whether that's our 160 or our 140, or our 120, I'm sorry, and let's just say this is 140, we would accept that null hypothesis if it was outside of that range. Well, I can't draw an H. Anyways, now let's talk about alpha values versus p-values. So an alpha value is the predetermined value in an experiment, which kind of dictates the probability that you've rejected a null hypothesis and that this is true. I can explain that a little more with this chart up here. It's a little abstract, but what I think is a lot more kind of straightforward is what a p-value is. So p-value just represents the alpha value. Let's say we have a study and we want to be like 95% confident with our results. This essentially is our alpha is our 95 in this case, but 1 minus alpha, so 1 minus 0.95 because 95% is 0.95 equals 0.05. This is our p-value. And this is essentially if something is higher than our p-value. So let's say we have a result with or an experiment with a result of like 0.3. If this is higher than our p-value, we would reject the null hypothesis, or we'd accept the null hypothesis because we didn't quite get past that threshold of that 0.05. We need that value to be less than our p-value because lower means better. It means we had a stronger experiment. A way to think about this is, let's say we have a 99% alpha. This would have a p-value of 0.01. This would mean we are 99% sure that our experiment will have a value that is outside. That means that if we are 99% confidence if our tested value is lower than our p-value, then our experiment has a chance, 99% chance of being correct. It's a little abstract, but essentially all you need to know is that lower p-value is better. Now let's talk about power of an experiment. Power is a little bit different, just in the sense that it's not as straightforward as like selecting an alpha value, because the alpha is something you select. The beta is more something that comes along naturally with like the strength of a test. All you need to know though is this equation for power equals 1 minus beta. So let's say your beta is stated to be like 15% in an experiment. Your power would then be 0.85% because 1 minus 0.15 is 0.85. So now let's talk about types of error. Type 1 error is essentially like false positive. That's how I think about it. So it's you reject a null hypothesis, meaning you think something's significant when in fact it's not statistically significant. And type 2 error, on the other hand, is false negative. So you accept the null hypothesis, you don't think anything significant is going on when there actually is. So again, just those terms. I like thinking false positive, false negative. That's easier for me. If we get this on an exam, it'll probably be like multiple choice. So I don't think it's ever, and it kind of helps you in like setting up an experiment, but like these errors will only occur in like, let's say, let's come back to this 95. We'll basically get either a false positive or a false negative 5% of the time. But you know, like a 19 out of 20 chance of getting something right is generally like really good. So that's just kind of like we accept this at a certain rate. And for most people, that threshold is 0.05 for most scientists. Let's talk about z-scores now. So z-scores are, this kind of goes back to standard deviation. It's kind of like how many standard deviations something is away from the mean. So that's just what a z is, a z value, I should say. as opposed to like a z-score. So a z-value is, let's say, a standard deviation. I'm just going to make up, let's say this is 3. And let's say big X, our selected value, just from experiment, is equal to like 9. And let's say our population mean is equal to 6. If we set this up, 9 minus 6 is 3 over 3 equals 1. We have a z equals 1. That would be right here. And since these are measured in terms of standard deviations away from the mean, this essentially means that this tested value specifically, not all tested values, but just this one, is 1 standard deviation away from the mean. And that's all z is. Z-score is a little bit different. Same concept. So you could write this as big X or X bar. Doesn't really matter. And we still have our standard deviation, but it's in a different form here. It's in the form of the standard error of the mean. I believe on a previous slide, I kind of distinguished them. They're pretty much the same for the purposes of this, so don't worry about it too much. Just that standard deviation over your number of samples squared. So with this, it's essentially, this is all well and good. We know standard deviations, but now let's say we have a sample size of like, I'll say 9, because that's a number that divides really easily. So we have our X bar. We'll still say X is 9, and we'll still say mu is 6. So 9 minus 6 divided by 3, which is also divided by the square root of n. We said n is our population. It's 9. Square root of 9 is 3. Now we get 3. And the reason this number is different is we generally want this number to be bigger for the course of experiment, because that means it's significant. The z-value you're going to see more than anything for a two-tailed z-test, meaning it could either be higher than or lower than. This kind of goes back to our blood pressure example, where if we're looking for a product, or we're just looking for a change in significance, we're not looking for a change in a specific direction, we use a two-tailed test. And these would fall at 1.96. However, if we have 3 all the way over here, you can see that this is so much more far out. The odds of getting this are so much lower. That means this test is like significant generally. And that's what a z-score does. It's probably like the most basic statistical test, just in the sense that it works for a population. You can see that population mu right there. Generally, t-tests are used for samples just because they account for the inaccuracy of a sample a little bit more. But just in a basic model, your z-test is going to be your most basic way to kind of rate the power of an experiment and to see if a result is significant. Okay, so I kind of did an example on the last slide. I want to do a more comprehensive example on this slide, especially now that we have a blank graph. We have our z of 0.05. This is our z value. This is our test value we want to beat. And this is 1.96 standard deviations away from the mean with that two-tailed p-value of 0.05. So that'd be somewhere either over here, we have positive 1.96, or somewhere like right here, we have negative 1.96. You can see that's really close to like 2 standard deviations away from the mean. So essentially that should show you, if you remember like our 68-95 rule, that 95 is essentially, we're looking for the 5% of the population that falls outside of that. So that's kind of another part of where that comes from. We can really quick calculate our z-score just for this set of data. It's really nice because we kind of have everything we need right here. So we have 450 is the sample mean, minus mu, which is 500. This is the population mean. On the previous slide, I mentioned that you could use this to compare like a sample in a population to the population. You can also compare the mean of a sample to the population mean. And this is usually a little more what this is used for. But yeah, and then we can just divide this by the standard error, which is just the standard deviation, which in this case is 100, divided by the square root of n. Square root of 25 is 5. So we essentially just get negative 50 over 20. We get an answer of negative 2.5. So now if we come over here, negative 2.5 would be about right here. And this is beyond our negative 1.96. So in this case, this is statistically significant, just because essentially everything beyond this is statistically significant, and everything beyond this is statistically significant. And since we fell over here, we're in a significant zone. So that means that our product in this case is doing something. I forget what example problem I pulled this from. Something else we can do is we can see if a sample falls within the population mean using like an interval. So what we can do, or like a confidence interval. And something to note about confidence intervals is they will be different sizes primarily based on your z-value. What the z means in this case is there is a 95% chance that the population mean falls inside this confidence interval. And that's just due to the fact that like statistically we could be wrong, but it means that 19 out of 20 times our mean will be, the true population mean will be in this range if we don't know the true population mean, if we only have an estimate sample mean. So in this case, it's kind of like we're reverse engineering it to get the population mean, or at least what we think it could be. So knowing that, let's set up this problem. It's not too hard. We have our 450, because that's our x bar, plus or minus our z-score, which was 1.96. This isn't our, I shouldn't say z-score, sorry, or, yeah, no, because it's not our z observed, it's our z-value that we want here. So this is 1.96, because this is the z-value at 95%. Then we actually do times the standard error of the mean here instead of dividing. So we do times 100, because that's the standard deviation, divided by 5, because that's the square root of the number of samples. So here we have 450 minus 1.96 times 20. We get about 410 to plus 1.96 times 20. We get 490. And this means there's a 95% chance that the population mean would have fallen in here if this was like the same population. Something interesting here is since our population fell outside of the sample, this means the sample isn't likely from this population because the 500 falls outside of the bounds of this 490 from the thing we just created. So, or the confidence interval we just created. So that's another way you can kind of like check yourself. Although the z-score is already like not the most difficult statistical test to begin with, so you probably just save time just by doing that. But if you're asked about like a confidence interval, just remember your reliability coefficient is just your z score for that value. Standard error of the mean, standard deviation over n, or it could be sample standard deviation over the square root of n, square root here as well, and then your sample mean, which was 450. So now let's talk about clinical significance versus statistical significance. So statistical significance is what we've been talking about kind of for all of this lecture. It's when a treatment shows a correlation with positive effects that can be measured statistically. This would be like you have a z-score above your z-value for your selected confidence. Clinical significance is a little bit different. You don't per se need to be statistically significant to be clinically significant. Let's just say there has been a study done, there's a new, we'll go back to the hypertensive drug, and it's been shown in some patients to lower their blood pressure by 30%. Let's say in a lot of patients it doesn't really do anything, but there have been like several documented cases where it does, and it's never been shown to harm. That can be clinically significant depending on like the number of patients, obviously. Now, if it's only one patient has ever responded and had that 30% decrease in blood pressure, it's like, okay, this probably isn't real. But if it's like enough that it's kind of, it comes down to your clinical judgment, right? And that's something that, I mean, as a practitioner, or not as a practitioner, but as a healthcare professional, that will need to look at data to recommend treatments to doctors. This is something we should know. So it's just like, even if data isn't clinically significant, if there are positive results with low harms, it could be clinically significant. One last thing I want to talk about z-scores is a one-tailed test. So we've been talking about the two-tailed test value for z-scores. Um, you can see this z is a little bit lower as opposed to the two-tailed z-score was 1.96, meaning it was probably somewhere like over here, 0.96. This one's 1.65, which is, I don't know, I'm going to make it up. I'm going to say it's right there. So 1.65. Why is this? So the reason this is for the 1.65 score, which I've now decided I'm going to draw in blue instead. This area is everything over here is significant. It's still a value of 5%. Keep that in mind. But it's only on one side. Our value of 1.96, however, is on two sides. So even though the area is a little bit smaller, it starts a little bit smaller since there's two of them, the area I shaded in blue before I covered it up with red as well as both areas in red, are equal area, and that both equals 5% of the curve. Now, as you can imagine, in most cases, we kind of want to work with a one-tailed like t-test in real life because we don't want our significant result to usually be, oh, it actually raised blood pressure significantly. It's like, that's great that it does that, but practically, we kind of only want it to go one direction. So what would like a null hypothesis and an alternative hypothesis look like for a one-tailed test? So for a null, it'd be your H0. What do I want to do? Because blood pressure is a little counterintuitive, just in the sense that going down is good. So let's just say a drug that increases life expectancy. It's just a pill that makes you live longer. Easiest example I can think of. So for this, our null would be, our mean is less than or equal to 0 extra years of life expectancy. So what does this mean? It means it might just not do anything. It could be a sugar pill. It could alternatively make you live less long. So the mean here could be a negative number. So not great. The alternative, however, in this case would be mu is greater than 0, in the case that it would make you live longer. So in a one-tailed test, you're going to have one greater than or less than symbol in your alternative hypothesis, but you'll have a greater than or equal to or less than or equal to in your null hypothesis. And that's just kind of because you want to assume that there is no change, or it accounts for that negative change, which would be like on this side of the graph. And it's not just looking at the side of the graph, because if it goes far enough down, it could actively be bad. And that's something we need to like take into account when we're making medications. All right, that's enough z-tests. Now let's talk about t-tests. Um, T-tests are used when the sample size is really small generally. Rule of thumb, if it's less than 30, at least this is how it works in most statistical classes. I don't know for sure if Dr. Go uses this definition. This isn't from in class. This is just something I knew coming into class. Less than 30, less than or equal to 30 generally indicates a t-test. So even if it's a sample size of like 25 and he tells us on the exam to use a z-test, just use the z-test, even if he really should use a t-test. Although I can't imagine he does that, to be honest. So you can see that t is super similar to calculating a z-score, because remember our standard error is our standard deviation, which in this case, since it's a sample, it's the s and not the sigma, divided by the number of samples. So to just get a t-value, it's pretty simple. So let's just work through this problem here. We have our sample standard deviation as well as our number of samples. It doesn't give us that directly, but we know 30 bottles, so we can assume sample size 30, x bar, and mu. Something else to note here is degrees of freedom. Now, where degrees of freedom take place in this isn't actually in the standard error. Well, it is, in the sense that this sample standard deviation right here already had it calculated. Remember the sum of x minus mu squared over n minus 1 is sample. Another place it takes into account in a t-test is t-test specifically, unlike z-test, on their chart will also have number of samples. And when you're selecting that value, it's important to remember n minus 1. So even though we have 30 samples, on a t-chart, we'd actually be looking at sample number 29. And we'd still be doing 0.05% confidence because that's on there. There's basically just like 2 rows that we would select from for that reason. And for that, I just pulled that t-value from a t-table because I didn't want to spend the time looking it up while I was recording this. It's 2.045. So if we get a number that is greater than 2.045, then we know it's statistically significant. So now we could just do the math, honestly. X bar is 120.05 minus mu, which is 120, divided by our standard error, which in this case the standard deviation portion is 0.84, divided by the square root of our number of samples, which is 30. It's not n minus 1 just because since this standard deviation right here already has it calced in, like we talked about, it's just 30. Let me plug that in my calculator really quick. 0.5 divided by 0.84 divided by 7 squared, 30. And we get a final value of 0.33. Now, since 0.33 is less than that 2.045, we will accept the null hypothesis. So accept null. And this has similar, same principles of accepting, rejecting null hypothesis as like a z-score will. Just since this number is lower, it's not statistically significant. So yeah, that's pretty much all there is there. Okay, so similarly to z-test, t-test also have confidence intervals they can work with. This is when you don't know the population mean. So this is the same problem from the last slide. It's just we don't have, just kidding, we do have mu now. But let's pretend like we don't. So we have our, and this is essentially seeing if the population, it's predicting if the population mean will fall into this sample. And since it's a 95% confidence interval, there's a 95% chance it will, if it's not statistically significant. So we have our x bar, so that's 120.05, plus or minus our t-value. This isn't the t-value we calculated, like this isn't our t-score, this is just the t-value, and that was that 2.045, just that standard value from a t-table, times our standard deviation, 0.84 over square root 30. And then this is actually already calculated down here, so I'm not going to solve this out. You get 119.7 is a sin mu, and it's also 120.4. And this is for a 95% interval. Now you can see here that our actual mu is 120, which does fall in this range. And this means that this is not statistically significant. This is kind of the opposite of the z-score confidence interval we calculated, because that z-score population mean fell outside of it, meaning there was some statistical significance. This one's the opposite. This one falls inside, so there's not statistical significance. So we accept H0. And in case I didn't say it on the slide where we calculated the z confidence interval, we would reject the H0 there. This next problem is like a 2-sample t-test. It's a little tedious, I'm not going to lie, but it is at least not incredibly hard. The hardest part is calculating this what's called pooled variance. Pooled variance. Let me not cross it out this time. Okay, how do we solve this? So it's pretty simple, at least in theory. It's just a lot of work. We have, I guess one thing I'll talk about first is this is a little interesting because it's new. You can see this number of samples in one condition plus the number of samples in another condition minus 2. This is the first time in this class we've seen a degree of freedom of 2. And that's really just because we are dealing with 2 samples. So it makes sense that we have 2 degrees of freedom there. So your pooled variance is the first thing you calculate. It is your number of samples in condition 1. So for this problem up here, this would be 24. So we have 24 minus 1 times your sample standard deviation squared. So up here, we'll just say this is sample 1 for the sake of convenience, 6.14 squared. Then this is plus your sample standard or your sample size minus 1 again. So for this one, it just also happens to be 24. It doesn't necessarily need to be. I don't believe it changes the math. I believe as long as you are consistent with where you, as long as you differentiate your standard deviations, it shouldn't matter. So 24 minus 1. And in this case, the standard deviation is 8.09. So for example, if this had been a different sample size, like let's say the sample size had been 22 minus 1, I would really want to make sure this 8.09 is paired with this number, because otherwise it's going to throw off the results. And then all of this divided by n1 plus n2 minus 2. So this is 24 plus 24 minus 2. So I'm going to plug this into my calculator really quick. In this denominator, we have 46 because 48 minus 2 is 46. Then for everything else, it's 23 because 24 minus 1 is 23 times 6.14 squared plus 23 times 8.09 squared. Divided by 46, we get this number of 51.57. And the last caveat here is that this SP is actually squared. Actually, that doesn't matter too much because it's squared in this equation as well. So we could technically just leave it that way as long as we remember to leave it that it is squared and not to square it again. So I'm just going to do that because that makes my life a little bit easier. So for this t-value, oh, I forgot to mention, by the way, this is the t-value for this problem. It's based off the sample size of n minus 1, so 24 minus 1, 23, and it's still a 95% confidence interval. So just so you know. Or actually, no, I'm sorry, I did that backwards. This is a value of 46. It is, it's equivalent to this right here. Yeah, so since we're essentially basing the t off samples from both sizes, and t-charts don't usually go up to 46. I remember when I was first setting up this problem in this PowerPoint, I had to like do a specific t-score calculator or like t-value calculator because most of them after 30 go in intervals of 10 because again, you don't usually use t-scores for samples greater than 30, but this problem just happened to, so I needed to Google it. So hopefully that doesn't happen on the exam. Yeah, this is a t of 48 minus 2, so 46. Sorry about that. So with enough stalling out of the way now, we'll just say x1 is sample 1 and x2 is sample 2 just because that's what we've been doing. So the mean for the top one is 127 minus 136.54. And then this is all divided by the square root of our pooled variance, which we calculated to be 51.7, or at least that's the squared version of our pooled variance. So 51.57 divided by n1 is 24 plus 51.57 divided by 24 again because the n's are the same. N1's the same as n2. Plug that in my calculator really quick. So we get this as 2.07 divided by 127 minus 36.54. Divided by 2.07. We get a value of, or actually, we get a final value of negative 4.6. But I'll calculate this really quick because I kind of skipped this step in my calculator. So 127 minus 136.54. Okay, that's negative 9.54. And so we can see here, and we can assume this t-value is negative. We can assume we're doing like a, or actually no, this is a two-tailed t-test. I do want to specify that because we just wanted to see if these populations were different. So basically drawing this on a normal distribution, we'd have a t-value of like 2 somewhere over here, -2 somewhere over here. Then we'd have our value of -4 like all the way over here, -4.6. So this is pretty significant. We can say pretty confidently that these two don't belong to the same sample, just based on how statistically significant they are. You might also have seen this hypothesis thing I included for this. This is a pretty good hypothesis like formula for a two-sample t-test. Essentially all that it means when we're like comparing means like this is that if u1 equals u2, that means the means are about the same significantly. And if they're not about the same, then that means we can do the alternative, which in this case, it's kind of obvious, right? Like 127 is pretty far away from 136, especially when that many samples are doing it, consistently. Okay, so now let's move into the final type of problem we might see on the first exam. This is what's called a paired t-test. Essentially what this is solving for is, and this is probably one of the more clinically relevant things for us if we were designing a test, because it shows if there's a significant difference between two groups of means. So what do I mean by that? This example, Dr. Go kind of went over it in class, but like obviously when he's not working out the exact problem, it can be a little harder to follow. Basically, we have two sets of values. We have blood pressures of a drug that were taken before administration of a drug and blood pressures after. So we want to find out if this difference between these two groups is significant. So how do we do that? The formula for it is kind of deceptively simple. It's your t-value or your t observed equals the difference in means divided by the standard deviation of means over the square root of the number of samples. So compared to some of the other equations, at first glance, it doesn't seem incredibly difficult, but where this kind of problem solving comes in is with the standard definition of mean, or the standard deviation of means. This is by far probably the hardest thing to calculate, at least on this first exam, but I will go through it. Before we talk about that, though, let's talk about some of the hypotheses for these. We have our null, which in this case is similar to things we've seen in the past. It's saying that our mean will be greater than or equal to 0. This means that there won't be a change in blood pressure, it'll be 0, or it will actually make it worse. Our alternative is that the mean will be less than 0. This means the blood pressure will be lower, it'll be better. And then I looked up the t-value for this preemptively. Remember that we have that n-1 degree of freedom. There's just drew 11 because that's the that's the t-value we have. We have 12 samples, so n-1 is 11. So in this case, n is 11 for this t of 0.05. That's the sample number, but we don't really need that for solving this. Because remember, we don't need to insert the degrees of freedom into this type of problem for the standard error of the mean. So now, after all that intro, we can get solving. So XD is really easy to calculate. When you have a group of tables like this is a little tedious, but you just need to kind of go through and calc the differences. So for example, the difference between 68 and 66 is -2. This is assuming you start with the after value and then go to the before value, which would make sense for a drug candidate. You want to see what the actual effect of the drug is, so you'd want to compare after to before. And if you calc all those, you add all of them up, it's -35. So for XD, it's XD equals -35 over, and then we'd have to do it over by the number of samples. This isn't n-1, this is just n, so this would just be over 12. Then if we plug that into our calculator, 35 divided by -12, you get an XD value of 2.92, -2.92. So we could just hold on to that number for a second. That's not the hard part of this problem, but it will come back when we're actually solving for the t observed value. Because remember, we need our significance value to be greater than this t observed, or our significant t, which is negative 1.795. So we're already off to a pretty good track with a mean that high, but obviously it comes down to the standard error. So let's just jump into this equation. I've been putting it off long enough. So to begin with, we have a few things. We have our number of samples. This is pretty easy. This is 12. Also in the denominator, we have it again as n and n minus 1. So that part's not too bad. Where you really need to be careful, though, is the sum of the squared of the differences as well as the sum of the differences squared. I really want to make this distinction because this can mess up this whole problem. The sum of the differences squared is essentially, since it's in parentheses, you are summing the differences squared. So over here, Dr. Go also gave us all the differences squared. In the homework problem, you need to calc this out yourself, which is a little tedious, but it is important for the problem. So in this case, this number is just 253. We don't technically need the squared because these differences are already squared since it's already in the parentheses. So we have 253. This, on the other hand, the squared is outside of the parentheses. So we have our sum of differences, which is this 35, this negative 35. So we minus negative 35, but then we square this because it's already been summed, and now we take the square. And since this negative right here is already always on the outside of the parentheses, you'll always be subtracting the first number from the second. So basically we have 253 minus 35 squared, but we also have an n out front here. So we have this 12, this n that comes from right there, and then this is all over n minus 1. So 12 over 12 minus 1 is 11, so just 12 times 11 in that denominator. And then I will calc that out really quick. So it's 12 times 253 minus 35 squared. And then we divide that by 12 times 11 times 11. We get 13.7. Now, as if this math still wasn't annoying enough, just tedious, we don't forget to take the square root of it, because this is the standard deviation squared. So if you take that, it's squared 13.7, you get 3.7. Okay, so now we can actually get solving the problem, finally. So if you remember, our x value was negative 2.92. 2.92 divided by 3.7, which we just calculated for this SD right here, divided by the square root of the number of samples. So that's square root of 12. So negative 2.92 divided by 3.7 divided by square root of 12. We get an answer of negative 2.73. Now, when we compare this to our t-value of negative 1.75, this is less than negative 1.795. So this is good. This means we have gotten our alternative hypothesis. Our blood pressure medication works because the value is lower significantly than this t-score we needed for this 5%, this 0.05% one-tailed t-test. And something else I wanted to stress, if I didn't stress this enough before, we do want to do a one-tailed t-test for this as opposed to two-tailed, just for the fact that if we did a two-tailed, we might find a significant result if the medication made it better, or if it made it worse. Which if we were just looking for a difference in general, then we could use a two-tailed. But since we're looking for a difference in a specific direction, this is why we do this. So yeah, since this value is lower than our negative value, and this is something you kind of need to judge for yourself, you always want in a one-tailed t-test, your value to be more extreme than it. So basically, if it's a negative value, like a negative t, you want your value to be like a higher or like number in magnitude more negative, and if it was positive, you want it to be a higher number while it's positive, if that makes sense. I think I just said that very poorly. Let me just draw it out. So let's say you had like a positive t-value of 1. You'd want it to be greater than 1. So you'd want a number like 2. Since it's negative 1, you want a value that is less than 1. You want negative 2. And that's just something you can kind of judge for yourself. And think about it like logically. Like if you want a drug to let's say raise alpha activity beyond a certain threshold, then you could like make it positive. But yeah, that's basically just how you solve this type of problem. So again, that's probably the hardest type of problem on this test. This next method is confidence intervals. They're a little bit easier. This is more of like a confirmation method to make sure you did your math right. This will show if your math kind of shows if your calculated value falls within the original population. So we have our negative 2.92, which we calculated before, plus or minus our t, which is 1.795, and our standard deviation, which was negative, it was 3.7, sorry. 3.7 divided by the square root of 12, because that was n. We plug all that into our calculator. Negative 2.92 minus 1.795. 0.7 divided by square root of 12. Get negative 4.8. I'm sorry, I believe this would technically be mu. At least for now, until we are able to prove or disprove it. Then calculating this other value, just in the opposite direction, this other one would be negative 1. So what we're able to see here is that since this value is always lower, this average, it means blood pressure will always be lower than a 95% confidence. Meaning we can safely say that this drug would generally always lower blood pressure 95% of the time, or 95% of the population. So that's really good. And again, it's just confirming, because we were able to tell that before with our t-test. But since this value, let's say this negative 1 instead had been like, let's say, like a positive 2, we might have still fallen in that range, but for when we're testing a drug like this specifically, we're able to specifically tell, okay, since the value is always negative, that means the blood pressure is always lower 95% of the time. So with that, that's the end of this video. Thank you so much for watching, and good luck on your exam.